Recording is rolling. It is Wednesday, October 23rd. Hey, that's mold day. So you guys have your lab write-ups out for the Centripetal Force Lab. Last week, you guys collected the data. Then we put the graphs together over a few days. And the last day was a little bit weird. We only got some class, but yeah. Anyway, we're going to finally get to score those. We still need to go back and talk about the water in the cup. Now, my other classes, I didn't get to that because yeah, but you guys great to do that. All right. Oh, I've got some new posters and demonstrations related to the lab you guys just did that we're trying to finish here. I want to talk a little bit about this progress check, Unit 2 progress check. You guys know I put the due date for this coming Monday, right? For that, right? Guys, now this progress check for Unit 2, most of the puzzles you can solve, I think there's about 20 puzzles or so. Most of these you can solve at this point. There's just a few that we haven't quite covered, but there's a couple of them I want to talk about today. You guys, this is one of those assignments that if you save it all for Sunday night, then it's going to be a huge headache. But if you do like, hey, yeah, maybe 4 or 5 puzzles today, 4 or 5 puzzles tomorrow, you'll knock it out like, oh, that was the breeze. That was no big problem at all. Right? And then of course a few of these can't quite do yet, but hopefully by the weekend I'll get you guys on this. Oh, quiz return. So you guys do have your quiz return. You guys got that. And so if you guys want to do corrections, I did post the solutions to Google Classroom. So solutions are on Google Classroom. So you guys can do quick corrections. All right. All right. All right. So I think that's the points good. Go. All right. So you guys ready to score your lab write-ups? Score your lab write-ups. All right. So. Okay. Let's go back to recap this lab. Keep the same. Gotta make this happen. So this was, you guys remember what was going on? You guys took this PVC pipe, you had some string, a couple of Play-Doh canisters, and your world was a round circle. And there was this balance between the weight of the one that was hanging, which is of course equal to this tension force. So maybe you could think of it sort of like that, right? Like how much tension force do you need to. There was this mass that was swinging around. You could possibly change that. You could change this radial size, and then there could be some speed set up to keep this all in. Well, the bottom one be true static equilibrium. It's not moving at all. But the top one you might call dynamic equilibrium, or because the radius was not changing. But that's not true static equilibrium because there's a net force because it's on a curved path. Anyway, there's these 4 variables. I split you guys up into different teams. Right? You guys have colored pencil on your desk. You guys ready to score this? All right, so let's go. Here, how about left to right? Right. So if you were saying, what's the relationship between this radial size and the speed? Okay, that's the one I got in this left column. That was the clubs. Okay. If you were okay, and of course you were controlling for the other 2 variables. So in that case, okay, the 2 canisters you wouldn't have been touching. If you had the spades, that's the middle column. That's between. Wait, okay. That would be the swinging mass and the speed. And then if you had the diamonds, you're looking for this hanging weight and this corresponding speed, right? Right. So for measuring tools, so everybody should have said either a meter stick or a ruler. You guys got something somehow to measure length, right, or radius, right? So somebody got to measure radius. Whether you were changing that or you're keeping that controlled, right? Somebody got to make a record of that. And a stopwatch. Right? You guys had a stopwatch to time how much time, right? So that you could calculate the speed. Right? That was true. Now this is true for everybody, right, guys? Everybody has the same measuring tools. I did also put scale on here, because if this was a free response question, you would have to have some way to get the mass. Now I didn't have access to a scale at the time, but I had you guys just add the masses together. I said, oh, it's this many grams for the empty canister, this many grams for the lab weight, but how many grams total, right? But this was a free response question. You'd have to mention a scale or a balance, right? All right, so there you go. There's your 3 measuring tools you can do the whole lab with. Okay, you guys got this? There's 1, 2, 3 points right there. Again, regardless of which version of the experiment you were doing. Okay, so everybody's got 3 points on the board. All right, 3 points for the measuring tools: ruler, a meter stick, a stopwatch, and a scale. All right. Also, the setup was the same for everybody too. It's the same lab setup. Right now, what you're going to do with that, how you're going to change it, is going to be different down the line. Right, but all I'm looking for is something like this. So these all say the same thing. It says, put a string through a plastic tube. Secure a safety bucket to each end of the string. Whirl the bucket, which is the swinging mass, so M swing, in a horizontal circle so that the weight of the other bucket, F hang, right, the hanging force, provides a centripetal force. Well, really, it's the tension that's a centripetal force. I could have reworded that a little bit. That's okay. That holds the swinging bucket in a circle of constant radius. Boom. That's it. That's all we're looking for the setup. So nothing fancy, right? Got a pipe with a string through it, a couple canisters, and swing in a circle. Boom. Done. That's it. Right. Of course, everybody's going to write it a little bit different. But does everybody have some kind of setup? Right. So give yourself a point if you describe the lab setup. Right. I think mine's just one sentence. Right. That's all it needs to be. Right. A couple sentences, maybe. Right. All right. Guys, ready to move on? Move on. So how'd it go? It was let's see, clubs, spades, and diamonds. All right. So we'll continue that. Here, I'll go ahead and make a little symbol here. We got clubs. We got spades. Okay, and diamonds. All right. All right, so let's see, okay, this next step also looks the same for everybody, I think, right? Which is you're going to measure the swinging mass with the scale, the hanging weight also with the scale. Although one of these you care about the mass, the other you care about the weight. You guys remember how you guys calculate the weight based on the mass, right? How do you go from mass to weight? You just multiply by Earth gravity, right? Like 9.8 meters per second squared or 10 meters per second squared, right? Right. So use the scale to measure the two canisters, and then get the radius of the horizontal circle with the ruler or the meter stick, right? You guys remember you held the meter stick up, right? Said, oh, what's the size of this radius, right? So go ahead and give yourself a couple of points for that, right? For use of the ruler or meter stick and use of the scale. Right? You had to mention how you were going to apply those things. So there's another 2 points right there. Again, that's the same for everybody. These are identical here. All right. This next step is also identical for all three setups, which is you're going to use the stopwatch to time 10 revolutions. So this says, with the stopwatch, time 10 revolutions and divide by 10 to determine the time period of one revolution. So there's 1 point for use of the stopwatch. Okay. Now, why did you do 10 revolutions and divide by 10? Why not just time one revolution?
Multiple trials.
Less error.
Yeah, okay, right.
Less error.
Less error with the stopwatch. Because guys, yeah, there's a lot of error with trying to like exactly start and stop the stopwatch. Right? Suppose it was an error of 1 second. Well, if it's one revolution, that's a pretty big error proportion wise. But if you did 10 revolutions and divide by 10, now your error also gets divided by 10. So now it's a lot smaller error. Yeah. So that would be why. All right, so guys, this is the same for everybody so far. Actually, this next step is the same too. Now, this next step you might have put in your analysis. It doesn't really matter if you put this in data or analysis, but somehow you got to get the speed. Guys, how did you get the tangential speed, the speed right here? Isn't it distance divided by time? The distance is one circumference. The time is however much time that took. Right? So give yourself a point if you said determine the speed or tangential velocity of the swinging mass by doing I have circumference divided by time period, which is 2 pi r divided by t, which actually I typed on your lab table anyway. So all you had to do is just say, oh, look, the equation's right there on your lab table. Might be right in front of you right now. Okay. So you guys give yourself a point for saying you're going to calculate the speed. All right. I threw in a step here that says square the speed to obtain v squared. That's really more of an analysis step that all of you ended up using, because remember, we were able to linearize all the graphs, but they were all related to v squared somehow. Okay. All right. Oh, guys, so far these have been identical all the way down, identical, right, including this next step. Repeat the previous steps 3 times to find an average speed. Right. So give yourself a point for multiple trials. So I told you guys that was always going to be a point too. Right. Multiple trials. Okay. In fact, before you guys started the lab, I handed you guys this quarter page. You guys remember this quarter page? Right? I told you exactly how to do the write-up. Right? There's some question, there's 3 different questions floating around, right? But so far it's been the same, right? List your measuring equipment, right? Procedure, describe the setup. We did that. Check. Use each tool to measure which variable. Check. Right? Identify independent and dependent variables and controls. Now we haven't mentioned that quite yet, but we're getting to it. Right? That's what's going to separate out, make your lab regs a little bit different. Multiple trials to reduce experimental uncertainty. That's one we just checked off right now. Okay. And then we'll go into analysis, which is going to be the graphs and conclusion here in a minute. Right. So you guys have that quarter page, gave you guys that. All right. All right. Right. So Right, so here's where these are different. So it's only this last little blip here that's different. Okay, so if you had the clubs, you wanted to say something like this. Repeat steps 2, 3, 5 for various values of R. Hey, so your radius would have been your independent variable. That's identifying the independent variable right there. Various values of the radius. Keeping the swinging mass and the hanging weight constant. Oh, well, there's your controls. Right? Of course, the speed would be different. That's your dependent variable. If you had the spades, you want to say repeat steps 2, 3, 5, or whatever steps on your paper, doesn't matter what the numbers are, for various values of the swinging mass, right? M swinging mass, keeping the radius and the hanging weight constant. Okay? If you had the diamonds, you want to say repeat steps blah, 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 for various values of the hanging weight, F sub hang, right? The hanging force, hanging weight. Right, which of course is equal to the string tension, keeping the swing mass and the radius constant. All right, so each one of these, depending on which card suit you had, right, you have a different independent variable and the other two control. Okay. Right, so give yourself a point if you identified your independent variable and your two controls. Of course, that's going to be a little different for everybody. Is there any question about what's what on that point? Okay, because if I put my pin down, everything above my pin was identical for everybody. And then below the pin, right now it's going to be a little different. Okay. All right, guys good? All right, next part. I put this in the analysis part. So AP likes to linearize graphs. I mean, we did a ton of linearization. Right, you guys have, well, you guys have, here's the conclusion look like this, right? Of course, you guys have these axes labeled and scaled, and you have points plotted and the whole deal, right? But this is like the overall shapes of these curves. Okay? So I got v squared versus weight, v squared versus 1 over the mass, v squared versus the radius, right? All linearized. That would be this analysis step. Okay, so if you had the clubs, you want to graph v squared versus r, right, which was the very bottom graph on the slide paper, right? So if you had the clubs, you would have had enough data yourself to go ahead and even do this bottom graph, right? That could come straight from your own data. If you had the spades, graph v squared versus 1 over the mass of the swinging canister, right? So v squared versus the reciprocal of the swinging mass, which was this middle graph right here. Right? So if you had the spades, you could have graphed this one all by yourself. Right? And finally, the diamonds, graph v squared versus the hanging weight, which was the top graph right here. Right? So if you had the diamonds, you could graph that top graph all by yourself. Right? Okay. Right. Here's ready for conclusion. All right, so conclusion. Here's the last point. This should be point number 12 right here. Right, point number 12. Right? Again, there's 3 different conclusions depending on which lab exactly you had. If you had the clubs, you could say the speed squared is directly proportional to the radius. So v squared is directly proportional to the radius for a swinging bucket and a horizontal circle with a constant centripetal force. Right? Right, that's if you had the clubs. If you had the spades, v squared is proportional to 1 over the swinging mass. So the reciprocal of the swinging mass for a swinging safety bucket held in horizontal circle, but also a constant centripetal force. And if you had the diamonds, v squared is directly proportional to that centripetal force for a swinging safety bucket in a horizontal circle. Right? Now this one, the radius would have been constant and the swinging mass would have been constant. Right? And so for each one of these, I'm talking about some kind of direct relationship for manipulated variables. Okay. So you guys know what directly proportional means. It means if you double one, you're going to double the other. Right? So like v squared proportional to r. That means if you double the r, the v squared gets doubled. Not the v, but the v squared. If v squared is proportional to 1 over m, then if you double the 1 over m, you're going to double the v squared. Okay? And then if v squared is directly proportional to the force, well, if you double the force, it's going to double the v squared, not the v, but the v squared. Okay? All right. That should be all 12 points right there. All right, you guys got yourself scored out of 12? Okay. All right. So hang on to that right now. Just before you walk out of class, I'll have you guys turn that into the grade tray. Now, as long as you have, here, you guys have all your data, of course, from last week. You guys got all the graphs, which we took a couple of days to put together. And you guys have your write-up, and you guys have the write-up scored out of 12, right? So maybe you did like, I got 9 out of 12 or something like that. All right. All right, everybody good? Yeah. All right, so here, let's get to looking at these posters then. So I have a poster for, this is exactly your lab in a nutshell. This is it. Okay. So you can put this all together. In fact, go ahead, pick a line off your data table. I want try this out right now. I just, so my other classes worked out pretty good. Pick one line off your data table. You guys see, you have a whole table of data, don't you? You have at least 3, 4, 5, 6, 7 lines of data. Pick one line. Try this out. Put this to the test right now. Look at the mass of your swinging bucket. Type that in your calculator. You guys got a mass right there? Type a mass. Right. But here, maybe I'll do something a little risky. I'm going to try this myself on the recording right here. I got a calculator. I need a volunteer, though. Guys, who thinks they had pretty good data? Who had pretty good data, they think? Wants to volunteer their data? All right, let's go. Asher. All right, so you got one line picked out. What was one of your swinging masses? 26 grams. Okay, now if we're doing grams, this centripetal force will come out to millinewtons, but that's okay because this would also be millinewtons, right? What was, now if you look all the way at speed, that's the second to last column, the one that just says plain V. What was that speed equal to? 1.73 meters per second. Okay, so then I'm going to square that. So I got mv squared divided by, what was your radius for that one? 0.13 meters. Okay, right. So I got grams, meters per second, meters. Right. So I'm gonna hit enter right here. Right. I'm gonna cover this up. So I hit enter. When I hit enter, it tells me what is the centripetal force, which is the tension strain, which should be equal to the hanging weight. Right. So Asher, what was your hanging weight equal to in millinewtons for that one? But okay, but probably off by some order of magnitude, right? So something to do with the 5.6 you got, a 5.6, right? So calculator screens tell me 590 something. Ooh, 5.6, 5.9. That's really, really, really close. Is it? Okay. Oh, yeah. All right. So that worked right there. It should be like 590, 600 millinewtons right there. Yes, that worked. All right. You guys can try that too. Right. Oh, and hey, how do you go, guys? How do you go from force to acceleration? Think back a few weeks ago. What law of motion was that? Newton's second law of motion, wasn't it? Isn't acceleration just force divided by mass? Right, net force divided by mass. That's going from this box to this box. Look at that. Got centripetal acceleration. Actually, if you look on your AP equation bank, I can point this out. That's actually the one that AP puts on the equation bank. It's right. It's kind of near the top. You guys see centripetal acceleration equals v squared over r. Hey, that's that one right there. That's right there. But you guys do see the connection between these two boxes, right? Guys, here, let's do a story. Let's attach a story to this. What if you're a ladybug? You land right on this canister. Oh, I like this canister. This Play-Doh smells nice. And then you start swinging this around. Right. Do you guys feel those G's? You feel the G's, don't you? Because you're going around the curve. Right? How many G's? Hey, that's kind of this question right here. You can quantify the acceleration. All you have to do is say how fast you're going, square that, divide by the radius of curvature. Boom. How about this? You're in a car. You're going around a pretty tight curve. Right? You guys ever like leave the interstate and you're going a little too fast? It's like, slow down. Right? You're going around a curve a little too fast. Right? You feel like you're thrown to the side. How much? Hey, well, that's just this right here. Right? And if you got a friend in the passenger seat, you say the radius of curvature is about the same, 50, 60 meters, whatever that curvature is. Right? Everybody feels the same centripetal acceleration, even if you're different masses, because the mass canceled out, right? Because it's the acceleration, right? Right. All right. Let's see what else I got here. Now, let's go a step more detailed. Guys, look at this conical pendulum. This is really this same thing, but maybe more nuanced. You guys see you could swing that around, make a conical pendulum, right? So now this string is no longer horizontal. It's actually on some angle. And I can say quantify the angle from the vertical, right? Maybe something like that. Or you could do from the horizontal, but on this poster I have from the vertical. Okay. Now, how is this different from this? Well, with the flat string, isn't this picture on the left that we've been looking at just the same thing as this, but this angle theta goes all the way to 90 degrees, right? It would be that, right? I had you guys assume this picture on the left, but this picture on the left isn't true. I'm just assuming that the string tension is exactly horizontal. But wait a minute. I think you guys did a spring scale lab where similar to this, where it can't go straight horizontal because I left off a detail on this poster to simplify a little bit. Guys, did I leave off the weight of the swinging mass? I didn't even draw that. Look, I didn't even draw the weight. But it does have a weight, doesn't it? Right. But if the weight was small compared to the string tension, then, well, this would be pretty close. Should be pretty good, approximate enough to I'm working a lot. Actually, it is, right? Oh, yeah.
The centripetal force is equal.
Okay, is the centripetal force equal to the tension? Yeah, that's like the perfect question, right? Because that's what we're kind of teasing apart right now. I had you guys assume that it was, and I've been saying that all along the last few days. Oh, the tension is providing centripetal force, right? Now we're going a step more nuanced. Say, well, if you consider this weight, which if the swinging mass was pretty big, so that its weight actually was significant compared to this tension, right? Or if you're swinging it kind of slow, or both, because those kind of go hand in hand. If you have a really heavy swinging mass up here, you do have to slow it down a little bit. Isn't that true? Right. Then maybe this is more realistically what it would look like. In which case, the centripetal force and the tension are no longer exactly the same thing. Right. So it's a little bit more nuanced take on this. Right? Guys, let's see if you guys are following. This mass that's swinging around, how many individual forces are acting on this swinging mass right here? How many forces? I see two. I see two forces. Guys, you might get a free response question that asks exactly what I just asked you. And they're looking for two forces. The weight and the tension force. That's it. Those are the only two forces. The weight pulls straight down. The tension force pulls off on an angle up to the left in this case. Okay. Right. Now, if you want to do some more analysis, suppose I introduce a Cartesian system aligned vertical and horizontal. Right? So the weight's already aligned. This tension force I can break into components. Say, well, how much up does this tension force pull? And how much in does this tension force pull? You guys see that? Do you guys think how much it pulls up actually does have to cancel out with the weight down here? You guys see that? Right? Which is actually what this says right here. So if you're playing off the angle from the vertical, then that would be a cosine component. Ooh, is this dash vector right here? This dash component? Isn't that just a cosine component? Oh wow. I just noticed I put this arrow backwards. Wow, I can't believe I never saw that. Huh. I have to fix that. I have to fix that on my poster. Oops. Right. So anyway, but the magnitude is correct because it has to balance out the weight. That's what this says right here. Right? And then this Ft sine theta. Well, okay, here's my full tension force. Sine theta, that would refer to this component here. Isn't that the net force? Right? And there is a net force on this mass. It is not in equilibrium, not in true static equilibrium. There's a net force. Hey, and that net force is the centripetal force. And that's what this box is down here. You guys see that? Right? So you could do like a system of equations. If you, I checked AP Classroom, I see some students are already answering those questions. I think at least one of you already submitted it even, right? I forget who. But one of the questions looks a lot like this. One of the questions looks a lot like this. And I forget exactly what they asked you, but basically if you do the system of equations, there's so many questions you can ask from that, right? I forget if it was a proportion question or solve something exact question, but something like that. Okay. All right, guys good? All right, so next poster. If you're keeping track, by this point in this class, there's actually 3 different types of acceleration. Right? And they have different units sometimes. They're different concepts, act in different directions. Right, so let's do a recap. If I go back to August, do you guys see this green one down here? It says, okay, tangential acceleration. Okay, this is a linear type acceleration. That's the first acceleration I taught you guys that we've been doing for most of this class anyway. So this could be like speeding up or slowing down in a straight line, right? So, hey, what if this was a big old circular racetrack and you're in a car going around a circular racetrack, right? What if you slam the gas pedal to speed up as you're going around, or slam the brakes so you slow down as you're going around? Okay, that's like what this is, right? And so it's the rate change in linear velocity, be like that. Okay. Now, if it's a whole turntable turning, you guys know how to get that too. And that's, right. You guys remember the tangential acceleration is just has to do with this angular acceleration times your location from the center. You guys remember that with the 3 Roosevelts sitting on there? You guys remember that? Right. Which I put right down here. It's the same thing. Right? Which actually connects to this next one, which is pink one right here. Alpha, I'm now using this week for angular acceleration. This is the whole turntable speeding up or slowing down. Guys, if tangential acceleration had units of meters per second squared, you guys know that. Okay, that's hammered. What are the units for angular acceleration? The whole turntable speeding up or slowing down spinning. Radians per second squared. You guys remember radians per second squared? Okay. So radians per second is just how fast is it spinning. Okay. Radians per second squared is if the whole thing is speeding up or slowing down spinning. Ooh, you guys remember that? Okay. Right? Like if the Earth is always going one revolution every 24 hours, you could call this about zero, right? Good. Okay, because it's not speeding up or slowing down the Earth. Right? Okay. And finally, this yellow one on the left side, centripetal acceleration. This is the one I just showed you for the first time today. That's this bottom box right here. Right? That's like if you're going around a curve, how many G's do you feel? You could answer with something like this. And oh look, guys, look at the direction of this because centripetal force. Like if I go back to the string tension, guys, centripetal force always pulls you which way? To the center of the circle. Center of the circle. Right? Like guys, if you cut the string right here, which way would this mass fly off? So it's going around a circle, and you cut the string. Which way would this mass fly off? Would it fly here? I'll give you guys an option. Let's see, show of hands. Here's your two options. Does it get right here? Does it make a sudden 90-degree turn and start flying straight away? Or does it follow Newton's first law of motion and just keep going in a tangent to its path? How many of you guys think? Show of hands. How many of you guys think it's going to be, it looks like a string broke. I'm going to make a 90-degree turn and fly straight away. Who says that? Nobody says that. How many guys, show of hands, say when you cut the strings, it's going to go in a nice straight line following its tangential velocity? Yeah, everybody says that. Everybody says that, right? That's what it would do, right? So there's some force preventing it from doing that. If it doesn't do that, as long as there's tension in the string, which is always pulling in. Divide by the mass, you get this acceleration. The acceleration always pulls you straight in towards the center, right? Okay. Now, if you're along for the ride, if you're on this curved path and you're blindfolded, it feels like you're being thrown which way? Does it feel like you're being thrown out? I might call it centrifugal, right? But from an inertial frame of reference, there is no outward acting force, right? There's only this inward acting force that's preventing you from following the straight line path that you would want to follow, right? Like if you jumped off, you would fly off this way. Okay. Okay. I got some equations here to show you how these are sort of related to each other. Okay? But it's three different types of accelerations, different units. Okay? Meters per second squared, radians per second squared, and then back to meters per second squared. Okay. All right, everybody good? That's good. All right. So this one was helpful to relate maybe some of those. It could be. Okay, you go back and forth. Okay. All right. You know what I haven't talked about yet? I haven't shown you guys the solution to the cup of water. Okay, let's do this again real fast because I can do this real fast. Put some water in the cup. I think I did this with you guys, I think last week, was it? Okay, water in the cup. Okay, it's got a string on it. Ooh, string, look at this. Okay, I said, how can I turn this upside down without the water falling out? You guys said, oh, just like swing it in a vertical circle. Ooh. Okay. So, yeah, in a vertical circle, look, all the water's staying in the cup. But what if I go a little slower, and a little slower, and a little slower? You guys think at some point it's going to go too slow and the water's going to fall out of the cup? You guys think, I wonder what is the minimum speed? Well, this is a centripetal force type question. So at this point in the class, we can answer that. I have a poster for that. So it's going to look like this. Okay, so here it goes around in a circle. Now I'm looking at two locations, the bottom and the top, but really for this particular question, all I care about is what's going on at the very top. Okay, guess that. Okay. Now, what if instead of a ball on a string, here this could be a ball on a string. Okay. Actually, let's talk about the ball on the string for a moment. Okay. If you have a ball on a string going around that vertical loop, and you're asked at the very top, draw a free body diagram. Here's what are the two forces acting on the ball on the string at the top of the loop? Yeah, tension and its own weight. Right. So its weight I labeled mg, and there's probably some tension force up there, right? Or is there? Ooh, wait a minute. Guys, what if you do a little slower and a little slower and a little slower until finally the speed at the top is just the minimum speed and just barely gets around. Guess what happens to that string tension? What does it approach? 0, right? And in which case you still have the weight, but only its weight would be keeping it on this curved path just for that one instant, right? Oh, because what if you were a ladybug and you landed on that ball and you're along for the ride? How do you feel for that one instant? It just barely gets around the top. Weightless, yeah, right. But no, that would only last for one instant, but that would be true. Right? Now, you could change the story a little bit. You could make this a cup and put some water in the cup. Now the cup's upside down. You guys see the water in the cup? It's all collected. Now the bottom of the cup is on the top of the paper, right? And maybe this tension force is now a normal force from the bottom of the cup that's holding the water in, right? But same thing, same story as before. Is if you swing this a little slower, at some point it's going to feel weightless. Right? So, hey, what if you were a goldfish swimming around inside this water in the cup? Could you feel weightless for one instant? Right? I think so. Right? If it just barely gets around. Right? So we're going to let this tension or the normal force, if you like the cup of water, go to 0. We're going to say only the weight is acting as the net force, which would be the centripetal force, wouldn't it? Right? Now, what does this look like in terms of equations? Right. So I can say the net force at the top would be, well, in general, it's the sum of the weight and the tension or the normal force, depending on what story you go with. Right? But we're going to let this tension or normal force go to 0 so that it barely gets around. And we're going to solve for the minimum speed. Wait a minute. How can I solve for minimal speed? Where's v in this equation? Hey, I know how to get v in this equation. Who knows how to get v, the speed in that equation? Centripetal force. Centripetal force. Guys, this net force would be acting as a centripetal force for some kind of circular path, wouldn't it? What expression am I going to substitute right there? mv squared over r, right? mv squared over r. Isn't that exactly what we just did a few minutes ago? Yeah, let's flip back a few posters. I mean, you guys are writing this in your notes, right? I see you guys writing this in your notes. Yeah. Okay. This one right here. That was the answer to your lab. Right? We had to do your lab before I could answer the water in the cup question, because we're about to plug that in right here. Right? So we're gonna take the answer from your lab, plug it in right there. Oh, there's your mv squared over r. Right? So okay, if you mean the speed at the top, now the speed might be. Here's a real nuanced point. Do you think the speed could possibly be constant or could possibly be changing? Right? Like do you think more realistically, if this is a vertical loop, it might be kind of slowing down on the way up and speeding up on the way down, right? Don't worry about that so much. I'm just kind of planting an idea that might show up in the future, right? But not we're working that. We're just going to focus on the speed at the top. Okay, so mv top squared over r, mv squared over r equals, right? And again, we're letting the tension of the string or the normal force from the bottom of the cup go to 0 so that we can solve for a minimum speed. Right? You guys get that? Right? Could you guys do the algebra and solve for that v? Right, so this bit 0 that goes away. Ooh, guys, what's going to cancel out? What cancels out on both sides? The mass. Now, what does that mean? Because when you see something cancel in physics, right? Here, suppose I put some water in this cup, swing around a vertical circle, and it takes like some minimum speed to get around the top. Then I go back and I put in like twice the amount of water. Ooh, that's a lot more water. That's a lot heavier. That's a lot heavier. Do I have to swing it faster or slower or the same speed to get it around the top? Same speed, because the mass is about to be canceling out right here, right? That's what that means. You guys get that? The fact that mass cancels out, it's not part of the equation, as long as it doesn't really change the radial size. Okay. All right. Let's swap the story. Right. Here, I'll show you guys the answer. Or you guys tell me, guys. I got covered up in this box. I got v minimum equals, and there's a short expression. Who solved it? Who solved it in their notes? Who's got it? V minimum equals what? Ah. All right, Jack got it. Boom. Exactly. There you go. That's it. Right. So again, the mass canceled out. Right? How about this? Who's ever been on a roller coaster? Goes through a vertical loop. You guys ever been on a roller coaster goes through a vertical loop? How fast do you have to go to make sure that you don't fall out of your seat? Right there. If you know the radius of that loop, right, and you know the gravity field of the Earth, that's all you need. Right? How about this? Design a roller coaster, goes through a vertical loop. We're good. Oh, yeah.
Isn't that if you're not like held in? Is that if you're just sitting there without a seatbelt?
Oh, yeah. If you don't have a seatbelt, yeah, that's true too. Yeah, they might strap you in just in case, right? But or like what if you had like a 1920s roller coaster and it was just on wheels and you didn't want to fall off the track and you had no safety measures? Yeah, we're gonna. All right. So yeah, we're getting a little simplification here, right? Right. How about this? We designed a new roller coaster. Goes through a vertical loop. No, we did an empty run, so we just got the empty cart itself. Okay, and we figure out, okay, it's gonna take some minimum speed. Okay, it barely gets around, but it gets around. That's okay. All right. And we stuff it full of passengers. Right now it's like twice as heavy because it's full of passengers. Right. And we send it on the run, and I see it's going the same speed as before. And I'm thinking, oh no, does it have to be going the same speed or faster or slower? Because it's full of passengers now. And you guys say it has to go how fast? Same speed. Yeah, because the mass, it doesn't matter if it's full of passengers or not, as long as you got the speed. Okay. Right. So all right. So you guys good with that one? Water in the cup, roller coaster. Okay. You know what? Here, let's do a little side adventure here. I always debate these little side adventures should we go on, but I'm gonna take some time. Here. Let's say we're looking at a 1920s roller coaster. It might actually look pretty much like a circle like that. Right? You could get this radial size. You could know the gravity of the Earth do that. Okay. But I bet when you guys have ridden on these roller coasters, they don't actually look like that. Right? I bet they look more like a teardrop type shape. I bet that's what they more look like. Right? Right. So, guys, why is the tear here? Let's draw a little roller coaster. Drawing right here, a little roller coaster cart. Right. Right. Why is the teardrop shape a better shape than an actual circle for a roller coaster? Huh? Oh yeah, it has to do with the G's you feel. Yeah. Right. Yeah. Okay, so guys, it goes like go back to this. Okay. So if I use either one of these as like a guiding equation, how much force, how much acceleration, like how many G's is like an acceleration. But if you hit like a true circle, it's like you're on this flat track. It's like you don't feel any G's, no G's, no G's. You're just going, just like you're in a car. Okay? And if you hit the circle, it's like bam, like you just run into this all of a sudden. Right? You go from nothing to a bunch of G's. Just it's really jarring. But with the teardrop shape, it builds up slowly. It's like I don't feel any G. Okay, feel a little bit. Ooh, kind of medium. Ooh, kind of a lot. Okay, so it builds up more slowly. So it's not like super jarring. Okay, it's a little engineering thing to think about. Right? But, hopefully that's something you can get out of this class too, is to think about puzzles like that and think, oh, how can I design it better? All right. Ooh, I've got this one right here. Again, I was reading you guys' progress check questions. Guys, there's a progress check question that can be answered basically from this poster. Like if you did not have this poster, it could be a really hard question. But if you have this one, you can solve it in like a minute. Well, here, if you really, let's go over this one a little bit. So let's say I got a car turning on a banked track. Guys, is that true? Maybe you're exiting the interstate. Don't they bank the track a little bit? Right? That off ramp, right? Because if it was flat, guys, if you had a flat road, what's the only force that would even allow you to make the turn? Friction. Looking for friction, right? Like if you had no friction. Hey, but what if the road is iced over? Is it really, really hard to make a turn if the road is iced over, right? Okay, so how could you maybe get some help from the geometry of the road? Oh, well, you can bank it, right? So do you guys see there's maybe some horizontal component of a normal force that could be helping you turn because it's providing a centripetal. This is a centripetal force. That's why I labeled it mv squared over r. Just this component right here. Ah, you see that? Right. I've seen that be an AP question in the past. Just that much. They say, what force could hold a car, allow a car to make a turn on a banked road? Right. What's the force? And the correct answer, again, going back a couple of years, I saw this question, was the answer was the horizontal component of the normal force. And you can see that right here. This was exactly the question and answer. Okay, is that? Suppose they want you to draw a free body diagram. How many individual forces on this car at this point? 2. Yeah, just the weight and the normal force. So this road might be iced over. This car is not making the turn because of any kind of friction at all. Right? I mean, you could maybe have some, but not this particular picture, right? Maybe this road is completely iced over. There's no help from any friction at all. Okay. How about this? Guys, which force is bigger? The normal force or the weight? And they're not the same. Which force is actually a little bit bigger than the other? You guys think normal force? Right? Hey, how about here's a little hint if you weren't sure. Suppose you were a passenger and you're blindfolded and you're going through that turn pretty fast. You're zipping through. You feel a little bit light or a little bit heavy? You feel a little bit heavy, right? Maybe that's a hint how this normal force is more than the weight, right? But anyway, so you set this up because most of the time inclines, did I tell you guys to introduce a Cartesian system parallel perpendicular to the surface, right? This is sort of an exception to that. So forget that rule for a moment. Let's go ahead and introduce a Cartesian system that's parallel perpendicular to gravity, right? Okay. And then I'm going to solve the rest of this one from here. So I'm going to break this normal force into components. And the vertical component has to hold up the weight of the car. You guys see that? Vertical component holds up the weight of the car. Okay. And the horizontal component of that normal force is the net force, which acts as a centripetal force. You guys see that? You can set up a system of equations just from that. All right, so what have we got over here? This mv squared over r bit is, all right, now here I did skip a little bit of step because I only got so much space on a poster, but this mg tan theta, I'm going to tell you guys exactly where that comes from. If this component right here is balancing out the mg, okay, it's equal to mg in magnitude, isn't it? This bit right here, okay? And I want to translate and figure out, well, how is that related to this component right here on the opposite side? It has to do with what is this angle, which is equal to this angle, same angle, right? This 31 degrees, okay? Guys, 2 legs of a right triangle have a what type of relationship? Sine, cosine, or tangent? Tangent. Okay, so if you start with the leg that's adjacent to the angle and you want the opposite leg, that's just multiplying by tangent. Hey, that's what this is right here. Do you guys see where that's coming from? Take this mg, do tan theta, you get this opposite side, which is the mv squared over r. Okay, that's it. So it's kind of a system of equations that led to that. Right. Right. But then, oh guys, what variable cancels out on both sides? The mass of the car. So if you were, for example, a road engineer, you're like, oh, I'm building a road up north where the road gets iced over every winter, and there's a bunch of cars. There's little itty bitty cars. There's like big old semis. Right? You got all different mass cars, all different mass vehicles, right? And I want to figure out how to bank the road to help them make the turn in the ice so they can still drive. The mass of the car doesn't matter at all. They all need the same banked road, and I could solve for that data. All I have to do is take an inverse tan of this expression right here. Actually, go from this, you just do a little algebra, you can get this box right here. Guess this, right? Again, give you guys a huge hit. See if you guys can figure this out from scratch. When you see this question in your progress check, see if you can take out just a blank piece of paper and solve it all from scratch, solve this whole thing. If you get really stuck, then I'm pretty sure this is one of your thumbnails, or I'm recording this right now anyway, so you can watch this video, okay? And then, I think the question they pitch at you guys is, they changed tangent of theta by some factor, which if you didn't know this, you'd be like, what? What are they even talking about? But if you have this in front of you, you'd be like, oh, okay, this I see how I saw that. Okay, I guess that. Right. There's another here. There's another one I want to help you guys out. You guys got your notes out, right? You guys got notes out. Here, I wrote this one up because this one's a little tricky. I'm gonna go back a unit to units. Well, here, sorry, used to be unit 2. Forces. You guys remember dynamics forces? The quiz I just passed out back to you guys. Right. So number 16 in the progress check. I had to sit down and sort out a little bit. It was a little bit tricky, but if you can get to the system of equations and you can do algebra, then it's actually not that hard from there. Right. Kind of the hard part is getting the system of equations. I'm just going to leave this up here for a minute, just enough time for you guys to write that down. Write this down in your notes. When you get to number 16 on the progress check, of course, see if you can solve it from scratch. And if you get really, really stuck, and you're like, I don't know how to solve this, then look at the system of equations that tells you exactly how to solve it. Okay. Yeah. Here, I'll do this. I'm gonna hold this a little closer. So, yeah, this is the best I can do. Yeah, I have no Zoom feature. we're gonna have to make do with that, I guess. Yeah, a little technology snafu. Actually, it's okay. I was having here while you guys are writing that down. Of course, having a new .cam, it works differently than the other one. I've also got a temporary laptop, so it's like, I guess it rains and pours, right? One thing fails, everything's gonna fail all at once. But we are living, we are making this happen. Okay. So see if you can figure out this from scratch. And if you get really, really stuck, then you can look at this and say, but remember, make sure you can make the connection so that you can get this from scratch. Okay, this is one of the harder questions they think they ask. Okay. All right, you guys good? All right. Oh, you know what else I meant to mention on this banked track, which is another question they ask also in your progress check. They actually have a coin going around like a funnel. Can you guys imagine like a 3D funnel and there's like a coin spin around? That's actually the question that pertains to this. All right. Do not have the great tray. Good. All right. All right. Let's try to fit in one more idea here. We got about 3 minutes. So you guys remember this going from linear to angular motion, vice versa, right? So here's a cool one. It's called O'Neill cylinder. So, here, how about this? Anybody watched a movie called 2001: Space Odyssey? Okay, so they got this in there. I think my students in the past always mentioned there's a game called Halo. I guess that has the same idea too. Anyway, suppose you're out in space. You have a big old ring. You give the spin. I think the movie Interstellar had one of these too. Right? It gives a big old spin. You think you could walk around on the inside and feel like there was gravity, but it wouldn't be real gravity; it'd be artificial gravity, wouldn't it? Right. So this is your centripetal force lab with this substituted in. Guys, instead of linear speed, what if I wanted like an angular speed? Could I just do v and divide by r? Right. Now I would normally take more time to do this, but I only got a couple minutes here. So try this out yourself. And if you start with centripetal force equals mv squared divided by r, and you substitute in omega times r for that v, then eventually you get this new expression. centripetal force equals m omega squared times r. Right. So, like you guys see this ladder going through the center. As you're walking up this ladder, guys, right at the center, as this thing's spinning, how much artificial gravity do you feel right at the center of this ladder? Zero. You'd be weightless. If you push off, you fly off into space. Right. If you climb down the ladder, it's going to feel like the gravity field, A equals omega squared times r, is building up proportional to the distance from the center. Right. And hey, I wonder if you could figure out how fast it's got to spin, so that if you know the radial size of this, you feel like one Earth gravity on outside. Could that be 9.8 meters per second squared here? Okay. Right. So yeah, next couple days we're going to be solving some puzzles. I still need to introduce actual universal gravitation to you. Let's hang that over there. So go ahead, turn in your lab with the lab right up to the grade tray. I'll get those in the grade book for you guys shortly. You guys have a good day.